Michael, you need to leave at 7, right?
Yeah.
You're good? All right.
Oh, you could.
If you have 4 participants.
Stronger person? Sure. We'll wait another 10 minutes before we get started. So for those of you who just got here, there's pizza right around the corner if you want some. So you can grab pizza or salad if you're hungry.
So they are like the same.
So it's one stream recording. So same time. Yeah.
Oh, that's
So I'll be back in a minute. Starting to talk at 5:45 if you want to like grab pizza or go use the restroom or anything. So.
Oh, you mentioned something that he's like it's coming Boston like a week. I don't think like yeah, I just talking to us like around like night, having
saw that we were talking about therapy. All right, I think we can give people 2 more minutes, 2 or 3 more minutes, and very cool.
Oh, you just want back?
Generally, it's like hello. They did a lot of projects.
So basically, you can oh, sweet.
So just do like quick trip.
Very nice.
All right, I think.
All right, everyone. Thank you all for coming here today. Really appreciate you taking time out of your lives on a Friday evening to come at these talks. I think we'll have 3 really good speakers talking to you about lots of cool things going on in kind of deep learning, digital health, protein design. So my hope is you'll get something interesting out of it and hopefully learn something. 2 hours, but I think the talk should only go for about an hour or so. So we can kind of take a break in the middle or mingle or whatever. So the goal really is to get people talking and excited about kind of using deep learning for chemistry and biology and health in general. So my hope is you'll have a lot of exciting conversations here and hopefully spur some interesting things. Now I do have one request from the department. They're going to get mad at us if we have any food in here. So if you have food in here, make sure to throw it outside and clean up after you're done. And if you can take a couple minutes to help us clean up the DeepChem stuff afterwards, really would appreciate that. I think we can start and kick it off. I'll now let Michael take over and tell us about some of the very cool benchmarking stuff he's been doing.
Hi, so good evening, everyone. I'm Michael, and I'm a second-year graduate here at Stanford at Chemistry Department. And thank you all for coming on this nice Friday evening. So I have been working in Pandy group here with Bart on DeepChem for about a year. So today I'm going to talk about this side project of DeepChem, which is called MoleculeNet. And this is like this, or everything I've been talking here has been already embedded into the DeepChem like module. You can simply like call the function in the DeepChem package. So MoleculeNet has been designed as a comprehensive benchmark for small molecules. So first, what is a benchmark? So benchmarking is a kind of standard testing for computational methods, and it has been widely applied in computer science field. So for example, there is a benchmark called ImageNet, which is like super famous, and it is a of like millions of figures. And also these figures are all tagged with like what kind of objects are in the figure and the boundary of these objects. And so what they do with ImageNet is like you have like a computer vision model, like a convolutional network. You test your model on all these data and try to compare your result with others and try to see like if your model is just like routine. On the other hand, ImageNet is like more than a data collection. There is an annual contest called iOS VRC, which is held by ImageNet, and all the big name we heard today of a convolutional network like VGGNet, like Residue Network, AlexNet, they all came from this contest. So in some senses here, we are building a benchmarking system. We are trying to mimic this development. We are trying to collect data of all kinds of like small molecules on building a platform. We would like people to test their model on our data, and we would like them to compare it. And to build this kind of a platform, we are encouraging and attracting more people to join us, like not only from computer science field, but also from chemistry field. We would like them to use our model to do their task. Okay, so wait, sorry. Okay, sorry. So today I'm going to talk about the framework of MoleculeNet, and I'm going to present some latest results. So MoleculeNet is like a benchmark. So the two core elements here are data sets and models. So data sets are like pairs of molecules and their properties. And we are using our models to kind of approximate this mapping from the molecule, from the structure of a molecule to its property. And in this process, like we have some kind of key steps there. So first, you have molecules. You need to like kind of pre-process it to make it machine readable. Then in this step, we are going to do featureizations and splittings. And after we make them into a kind of a readable form, we put them into the models to let model finish all the machine learning job. And after that, we are doing evaluation and we compare the results. So today, I'm going to elaborate on the first 4 steps, like data sets, from data sets through models. So first, let's look at data sets. So currently, the MoleculeNet benchmark is including around 17 data sets ready. And these data sets, according to their like properties, can be further kind of separated into 4 categories. So we have the very kind of microscopic level of property, mechanics property. And these QM series data sets, they are all about like atomization energy, HOMO, LUMO, polarizability, and ionization potential, this kind of stuff. And, oh, sorry. And a step above, we also have physical chemistry property. This is like solubility, solvent energy, like how the molecule interacting with water, with other solvent molecules. And one step forward, we also have very important biophysics tasks. So this is very important in drug discovery and all kinds of biological like research. So basically, it is touching about how molecules interacting with macromolecules in biology, like say protein ligand binding affinity. This is like PDB bind data sets about predicting the binding affinity according to the structure of your protein and your ligand. And we also have like pure ligand-based model data sets like the MUV and base, and have like a very microscopic level of properties. This is called, we're defining as like a physiology task, which means it is predicting the interaction between a molecule and the human body. So this is like toxicity. Like TOX21 is predicting how the molecule will interfering with your like internal pathways. So one core challenge about machine learning in chemistry is like we are caring about molecules, and molecules, they are having properties ranging from very microscopic to very microscopic. So the reason why we put this benchmark thing on is like, so basically you present a new model, and this model has been tested, say, on a quantum mechanics task. And we also want to try how this model is performing on the other 3 categories. And we would like to kind of find the application of this model. And say by using only one data set, you cannot do this. And by using a bunch, you can do that, definitely. So after acquiring these like data sets, molecules and their properties, we are doing learning. And how do we do that? We need to first transform a molecule into a machine-readable form, which is typically like a vector. And here, this process is what we call the featurization process. And we are changing this aniline model into a vector. We have now implemented around like 6 methods in DeepChem to do this. And in these 6 methods, I would like to kind of separate them into 2 kinds. One is called like the fixed length featurizer, and another is like variable length. So by saying fixed, we are saying that no matter how big this molecule is, we always make them into a vector of the same length. So the very famous example is like the ECFP. ECFP is like circular fingerprint, which means like you have a hash function. You are trying to hash every substructure in this molecule into in the final vector, and the vector is always fixed length, say 1024. And on the contrary, we also have variable length featurizer, like graph convolution and weave featurizer. So the point here is like aniline, it is like a molecule with a benzene and an amine group. So in total, it has 7 heavy molecules, 6 carbon and 1 nitrogen. And graph convolution featurizer will make a feature vector for each atom. So there will be in total 7 feature vectors here. And then for weave featurizer, we are looking at the pairwise interaction between these heavy atoms. So basically it has 7. So we have a 7 by 7 matrix. And each point in the matrix is like representing how these 2 specific atoms are interacting, if they are bonded, or how far they are in the molecule, these kind of things. So the difference here is that fixed length, we always have a fixed length vector. Variable length, we may have a set of vectors of different lengths, and this is related to our models. So after we get all these vectors, we are trying to learn them. So in a machine learning, you cannot put everything into your model. This will create like huge amount of overfitting. So instead, we are doing some kind of splitting. We are split all the data set into 3 subsets: train set and test set. Train set has been used to train the model. Then we use validation set to kind of optimize the model. Then we do the final evaluation on the test set. So one thing about chemistry is like you cannot just do random splitting everywhere, because like it maybe doesn't make sense in actual drug discovery. So what we do is we also propose some other kind of splitting method here. Here we would like to talk about these 3 kinds of. One is scaffold splitting. So scaffold means we are split the molecules according to their general 2D shape. So as you can see, in these like 10 molecules, all those with a benzene ring are in the train set. Validation on those with like an acyclic carbon chain. And then we're doing the final evaluation on cyclohexane, which is like totally different from your train set and valid set. And this way, we're kind of force the model to learn the chemical like instinct in there and trying to let them generalize to molecules they have never seen or not even similar molecules. So this is making the task like a much harder one. And Stratify Splitting is a bit different. So basically, we have a regression task. Performance stable, we may try to have the labels kind of sorted, and we kind of stratify it, which means like we have 1 to 5, which means lower, and then 6 to 10, which is higher. We separate them, we made them into 2 strata, and we do a random splitting in each strata, and then we combine them. So basically, this is guarantee. This could guarantee like all your 3 subsets, train, valid, test, have like their property value ranging from the minimum to the maximum. And the last one is time splitting. So this is specially designed for PDB buying. So basically, you maybe have data, and these data are not kind of acquired in like a single time point. They may be acquired from like a long time range. Say PDB buying, the data is to 1982 and to from 1982 to 2015. And what we're doing here is, suppose you are standing at this point, 2012. What you do is you use all your past experience to train your model. Then you optimize it according to your current like result. And then what you do is you are predicting the future. And this is like mimicking the actual development condition, which is like why it is meaningful in our case. So after we split, we have train, valid, and test. We are putting them into our actual models. So also like the featurizations, we would like to separate our models into 2 parts. DeepChem has now kind of having support for around 15 to 20 models, and we separate them into two parts. One is those conventional machine learning methods, which includes the famous like logistic regression, SVM, and also kernel-ridge regression, multitask networks. So the point about these conventional methods is that they are widely applied and they have been proved to be very useful. But on the other hand, they are not designed for chemistry data. They only accept fixed length data. It's like you have a figure, you have like a fingerprint from a molecule, you can import them into it too. But the thing is like they only accept fixed length, which means they are only corresponding to the fixed length featureizer we use. On the other hand, these graph-based methods, what we call them, is specially designed for graph, or we say specially designed for molecules. And this may including, now DeepChem has support for graph convolution, weave, anyone, DAG model, they may not be familiar. So the point here is like they're designed for graphs. So suppose you have like a molecule like this. You have these kind of 5 atoms, and we would like to kind of doing learning on this molecule, and we are trying to update the feature vector. So say in graph convolutional featureizer, you are having a feature vector for each atom. So now we would like to update the feature vector for this atom. What we do using graph convolution is that we trying to find the feature vector for all its neighbor atoms, and we combine them together and go through like a nonlinear function, and we go to the updated vector. And in a DAG model, DAG is like directed acyclic graph. We are making this molecule into a directed graph with all its bonds directed towards the central atom, like the one we would like to update. And then in this case, we will propagate all the feature vector from the farthest end to closer and then to closer. And then it's kind of like we're building a directed graph on this molecule, and we're using this way to kind of rationalize how this property are being like kind of connected with these bonds and with other atoms. So this is the difference. These conventional machine learning methods, they accept fixed length vector, while these graph-based methods, they are designed for molecules. They're designed for kind of learning based on your molecular structure. Here is the result. I have chosen like 2 datasets out of the 17, and TOX21 is like our famous classification dataset, and FreeSolve is like predicting the salvation energy, like a regression task. And what we see here is like these 2 bars corresponding to the weave in GraphCom, which are the 2 graph-based methods, they are outperforming all the other traditional methods. And this is what we want to see. And similarly, we can see in a free salvation dataset, message parsing neural net, weave, directed acyclic graph, and graph convolution. These corresponds to the 4 top bars. TOX21, we are using ROC AUC as the metric, so which means higher is better, so to the right. And for free salvation, we're using RMSE, which means lower is better, so it's also to the right. So basically, these 4 models are in the very right part, so we think they are the best model in this data set. So clearly, we can see graph models are outperforming all these traditional methods in like a bunch of different data sets. And let's take even a deeper look here. So here, we're trying to do an interesting experiment, like we're doing training with different size of training set. So we have 9 points here. So TOX21 in total have about 8K data points. And then what we do here is that we only use less than 1,000K points to do the training, and we do evaluate on the rest of them. Gradually increase the number of samples in the training set. We see how the performance increase. So the weave and GraphCom, they are on the top of all the lines, which meaning at the same with the same amount of training set, they are performing the best. And at the same time, let's try look at this multitask network line, which is like the blue line. So with 90% of the data point, it could reach about 0.8 ROC AUC. If we draw a horizontal line, here we can see with only 1/3 of the data sample, 30% of the whole data set, the weave and GraphCom could reach a similar level of accuracy, which means these models are way stronger than the traditional method. They only need 1/3 of the training sample of a traditional method to reach the similar level of accuracy. That is what we want to see. And similarly, free salvation, a regression task, lower is better. Similarly, single task network, at last it could reach about 1.5, and then 1.5 correspond to a 30% of data set too. And also the black dash line here is corresponding to the performances of basic ab initio prediction method. And what we see here is by using about 200 samples, our weave models could already kind of outperform these ab initio methods by using only these 200 samples. So this is it. So MoleculeNet is designed to be a benchmark. We would like to make a collection of all these data sets, and we test performances of different models on these data sets. We try to rationalize like which is better and how much better. So this is the work. We would like to encourage more people to use our benchmark to compare their model performances to ours. And we will always want to see a model can outperform all these models. Thank you.
Which of the splitting methods did you use?
So for talk splitting, for these two, we are only using random splitting. Yeah, as well.
While to specify which parameter or what the parameters are used, it seems that you just one slightly larger than
Oh, you mean hyperparameter? Oh, so basically we do like a Gaussian process hyperparameter optimization on all the model, all the combination of model and data set. So we just run like for each model and try to picking like the best performing. So all these models are already kind of optimized. Yeah. We do 20 runs of like Gaussian process optimization. Yeah.
How about the capacity of different models, like number of neurons in graph convolution, number of unknowns in logical regression?
Excuse me, can you say that again?
So how about the number of unknowns in different models? Like, are they kind of constant in different models, or they are very different in different models?
Different. Oh, sorry.
So you have number of unknown parameters.
Yeah,
right.
Oh, number of parameters. Okay, yes, I see. So basically, graph convolution is like a network, which means it has like filter. So actually, it has less like parameter comparing with like.
So filter size is less than the number of that you have.
Yeah, this depends on model. So basically, graph convolution is like a picking of like the convolution that we're using a filter, and filter basically has like less parameters to be trained.
Also, what about pooling? What kind of pooling you are using?
Oh, pooling? Yeah, we do use max pooling too in graph convolution.
How does the graph convolution work with molecules that have multiple rings?
Multiple
Do
rings?
you have experience of how you type molecules with multiple rings, multiple?
Oh yeah, definitely. So basically, we have data set which has like molecular range, like number of atoms ranging from 50 to 400, and graph convolution is like it can work on every molecule. Basically, you doesn't need to kind of specify the number of atoms in the molecule. Basically, it just do like it's like a fluid convolution.
Because my question is, if you have multiple rings in one molecule, some atoms could belong to two rings. So.
Oh, I see. Like two parts.
Yes.
So basically, what graph convolution do is like they do a bunch of like convolution network layers, feature vector for each atom, and then we do a final kind of averaging over all the atoms in the molecule. Yeah.
So this first thing, like the encoding part that you are using to convert, let's say, bulky atoms into vectors, that is also a neural network.
Yeah.
For the encoder or something. Some encoder.
Encoder.
Yeah.
Initial featurization. So the initial featurization part, we are kind of only using the atomic information. Like this is a carbon. So we will encode the information, this is a carbon, and how many bonds does it have, and like the hybridization state of this carbon, like this into the initial feature vector. Then we kind of update this feature vector step by step.
And how deep is the convolution network? How many layers you have?
How many layers? Okay, this is only on 2 layers. Yeah, only on with 2 layers.
So these implementations based on the Maxwellian chip graph convolution papers?
This is a paper from Harvard. Like, so I think the first author, the last name is Steven. Okay. And the weave model is like from the Stephen Kern's like graph convolution paper. It's like from our group. Yeah.
All right, let's take one more question if anyone has one. Any takers? All right, you're good. Let's thank Michael one more time.
How do these slides? Go before one, maybe? Yes, doesn't matter. And it's 2 times so far. Cool. And this is live streaming. No, that's Steve. Okay. Hey guys, Carlo. I'm CTO at Stratify, and we do protein development. And I'm going to try to convince you that though it's a little heretical to this crowd, it's not maybe as heretical as it sounds. So my background is in chemistry, so I like seeing structures and atoms and understanding all that, but then I was forced to go to grad school and work on this beast of a protein, which is a mammalian receptor notch. This thing is huge. It's like 290 kilodaltons. Nothing's crystallized about it. It's transmembrane. It's basically the worst possible thing you could possibly work with if you like chemistry. So we had to come up with ways to generalize about it and think about it. We just said, fine, we're just going to take the extracellular domain and we're going to say that binds to things. We're going to take this weird regulatory domain and say that regulates things. And we're going to take this intracellular domain and say that signals things. And so this kind of dividing up a protein that's very, very simplistic actually kind of worked. You can even go even farther and say this signaling domain yet is made of nuclear localization signals, transcriptional activators, something that induces degradation. And in this way, these components of a protein are composable. But in many cases it is. And if you kind of went back evolutionarily and looked at this receptor, you could see where biology actually itself had started to reduplicate things and had reused components elsewhere in order to create new functionality. And so we built a software platform and a company to try to reverse engineer and keep track of these functions at a primary amino acid sequence level, but not even at a primary amino acid sequence level, actually at a functional level. And this has proven itself to start to become really interesting. So here are a couple different proteins from a couple different perspectives, and every color you see is from a different organism. You start things like Cas9. The rate at which people have started to put out papers that use Cas9 to different effects and to more and more narrow effects has been increasing the complexity of these proteins based on the reusage and novel usage of domains that may have nothing to do with what you're actually thinking about. So there at the very end, the SABE, that's V4, I guess the 4 kind of got messed up there. It's the 4th version. So we're starting to version these new proteins, even though there is no structure of that entire protein. There are structures of some of the components, and some of these components do things just like bind double-stranded DNA, or bind the end of double-stranded DNA, or inhibit a protein. And yet these things are having to be engineered. And so what if you have to engineer these things, and it's useful to engineer these things, but you don't have access to a lot of the desired chemistries that you might want to have. And so we've tried to build out a system to make that as straightforward as possible, employ as we can some of these deep learning kinds of technologies to attack that primary sequence and that functionality as best we can. In the middle here, you have a switchable kinase. So you start with MEK1, a really important kinase in a human system, taking multiple years to scoot down the graph and to become complicated. A single paper, I think it's the Lin Lab actually here, is able to go from MEK1 to a light activatable kinase in one paper. But weeks ago, it's pretty sophisticated, and yet it uses 4 and 5 different organisms, protein domains, significant different effects. They did have the luxury of having crystal structures of these things and informing their designs, but at the end of the day, somebody actually had to go out and design that. And then at the bottom are just some more interesting proteins that have been designed that are extraordinarily complicated, again, without the luxury of actually having chemical structures. And so what we've tried to build is an abstraction layer, yet above that PDB structure, yet above the actual genetic sequence. You can start to talk about these proteins as components, as composable units. And it's very clear, we can't predict what actually will happen, but we can get you in the right direction. We can build pools of things, again, based on structuring the data in the ways that we have, that get you closer. Not 100%, but get you closer. top, we have a photo-switchable kinase here. You can kind of think about it as the red and yellow domains. They come together under ultraviolet light, and when you shine, then opens up, and the thing kind of looks like a kinase. And so when I would draw these out for a presentation like this, I kind of draw them in that way, where I have these domains, and I tell people the orange domain does this, the little green domain at the top sends it where I need it to go. I wouldn't think about it in this crazy DNA. And so we're trying to create a system where it's more like from what we built, where you actually have these domains that kind of correspond to what you're thinking about. You have functions that are both human and machine readable, that are associated with the entire protein, that are drawn from the individual proteins. And then there are other properties that we can also keep track of. So what we built is we have kind of three main components. We have a library of well, that's the frontest end, the library of annotated parts, where we pull in data as much as we can. At this point, much of that is very high quality data. It's annotated by us. Still relatively small, but it's enough to actually test out hypotheses and actually start work on. We have kind of some nice interfaces for building individual proteins, for building sets of proteins. So for instance, say you want a whole bunch of things at the N-terminus, you don't know which will work. You want a whole bunch of various linkers to try them out because you don't know which will work. You want a whole bunch of fluorophores because you want to try them out. Just put them in a row. It took you 2 minutes, and now you've built yourself 35 proteins. Hit buy. You don't have to worry about the DNA sequence. Mutations, things like that, we keep track of that. And then finally, we have our back end, which is this biologically aware API, where we're taking those kinds of functional domains, and we can start to ask biologically and chemically interesting questions of our data. A computer science person might want to ask them in a way that is quick. You can put them in for loops and run them great. But these are things like, what happens? Do you throw any exceptions if you put a signal sequence? If I want to order a protein such and such and such and such way, say, no, you can't put a signal sequence behind this. It'll throw an exception to your program. You can start to do analyses, not just design work with that API, but you can then do analyses on your own work. Give me all the proteins that have such and such function, that have the ability to go to the nucleus under certain conditions and in certain ways. Give me all the proteins that contain yet one of these other components. What does it cost to produce this protein? What is the intellectual property license landscape of this protein? So then you can start to use your programming, mix and match these things and start to say, look, I want to build something with this cost, this capability, I have this manufacturing throughput, and I want to avoid or I want to use certain kinds of licensed proteins. So we put all that together. Academically, this is actually free to use. Go online and use it. It's still relatively new, and we would like people to use it. So it's srotny.bio/pinecone, and I'll kind of briefly go through some of the more interesting parts of it. If I can do that, there's a screenshot. Best way to get there. Cool. So this is it. You can log in as you wish. Again, most simple function, let's just build a protein. I can click. There we go. So I just want to build a new protein. There we go. So we have our own library, and we've kind of tried to sort these things out, things that bind, things that light up, things that localize, etc. So we can just bind the things that we want. So get an antifreeze protein, something that binds to ice, I think. Let's go get ourselves a linker because we want to try that. Drag a linker in. And notice it's actually starting to keep track of the properties of the whole protein, something that fluoresces yellow. So very quickly, we built a new protein that's never been built before. If it will try again. It's hard to use here up on the stage. We built a protein. You don't know what the amino acid sequence is. In some sense, you don't care. You're going to try it out. You're going to see if it works. If you really want to know what the amino acid sequence is, it will tell you. It'll tell you what the DNA sequence is if you really, really want to know. We have references associated with this. If we want to start to build sets of proteins, that becomes just as easy. We can start to build out as much as you can afford to either buy or play with, where you can have as many domains as you like. So if you want to try a couple different linkers, try a couple different fluorophores, you have access to that. And again, this is not to replace any other analysis that you're doing, but to supplement it. So for instance, we have people we're working with where they do have access to some kinds of simulations and they want to figure out what is the kind of linkers that they want to use. And they come up with an answer. I want to try this one and this one and this one. Well, they still have to go out and build it. And so we have the ability to interface with them in that way. This is hard for me to use. The idea is, cannot keep track of the mouse as I, oh, I see. I can watch this side. There we go. So we've built now 3 proteins just by doing that. And as we can add more domains. Again, what this is a pretty nice one-dimensional CAD program. You're starting to build linear. It's a primary amino acid sequence, but you're keeping track of them in a related way. So these program, but each of those nodes have relationships to each other, not just the relationships of what you're building, but historical relationships. So you can start. So we've now built 6 proteins here. That's pretty straightforward and easy. But what we can now go do is, if we had questions about something. What's an interesting thing to have questions? Spider silk, that's pretty cool, but what's been used? Something common, hexahis, is just really easy. A hexahis tag. How has that been used before? I don't know. I'm new to the field. Very hard to use. We can ask questions of the data because it is so related. How has hexahis been used before? It looks like it's loading up. So we can say this will note that is the hexahis protein domain. We can then sort these things by various features. So within any given protein that has ever been used before, how has hexahis been used? You can start to get analyses. It's been used all up front. Wait, it's been used all at the back. What's the percentage it's been used where? How has it been used? How has it been used relative to other proteins? So you can start to ask these kinds of questions, run analyses on them. Get back results where it's not going to tell you the answer. It's not going to tell you what works, but it tells you, look, this has worked in the past. You might want to try that. And given your constraints, be they technical, be they design, be they manufacturing, you can start to apply those constraints. You can start to apply significant machine learning to this data, so you actually can run what instead of the 3-dimensional, very complicated system, in some sense becomes more straightforward, a 1-dimensional system. And we're trying to collect that data in a way that is so human and machine readable at the same time. That's what we built. We're looking for people to play around with it. We're looking to figure out what are the edge cases, what people really want to use it for. Yeah, thanks. Right. So there are certain features which are pretty well computed. You can actually compute what does a nuclear localization signal look like, and that's fairly straightforward for us to compute. We have ways to predict that, and then there are certain things that people always use. If you ever want to localize to a Golgi, you're just going to use the localization signal, and so you are able to actually ask of the program, I want a thing which localizes to the Golgi. You'll get access both to the things that people have used before, and if you try to import a sequence, a primary sequence that it is known or it will tell you, look, I'm pretty sure what you built will probably start to localize somewhere. So we try to bring in those biological features, try to insert ourselves between kind of that chemistry layer and that physiology layer.
What fraction of sequences are able to actually fall into the right set of domains? Without imagining that you have specialized
Certainly. I don't know the answer to that, and I know that there is a lot of things that you can build here which are not going to express. But there are also a lot of things that people have built, not knowing what the answers to those are, and they have worked. And so this is a way to peer into those things just purely from an empirical perspective. What has worked before, and how can we actually make use of that? Exactly. So as things actually have properties, you then are able to keep track of what those properties are. Additionally, we're starting to implement ways where you can run things like disorder So analyses, so you can start to say, look, this is the edge where there appears to be some disorder. There's probably some linker endogenously, so that's where I want to cut things up. And if I were to put these two proteins that have associated with them right next to each other, and that profile dramatically changes, even from a primary sequence perspective, we can say that we can tell you that might cause a problem. You might want to put a linker in there. So those are the kinds of things. Again, it's still empirical at the end of the day. You still have to test it. To help you and to inform you, even if you yourself are not an expert in that particular spot.
So how do you know all things that are synthesized? And how does it get?
We have people who are and pulling that in as easily as possible. And what we built is actually a pretty nice tool to import these things. So because we've had to import a lot of things, all you have to do is drop in a DNA sequence. It'll figure out, oh, this is actually this domain, this is this domain, this is this domain. So we can start to do that in a high throughput way. What we end up finding is that most constructs, if you go through AdGene or go through some of these other databases or other synthetic databases, once you've pulled in any domains, you just see the same ones over and over and over and over and over. Everybody uses the SV40 nuclear localization domain. So after a while, you're not actually pulling in a lot of new data. And then once people start building things, again, you can build very large libraries. Once they built them within the program, they remain in the program. So right now, there is a add to cart and buy button, and it ships it off to Twist or to GenScript or to somebody who's manufacturing the DNA. And we actually, because we design, especially if you're buying a pool of constructs, we design the DNA to be synthesized as individual chunks, which can then later be assembled. So you actually can save a lot of money having it done in that way, if you're intelligent about it. And then we also have ways to design cloning systems for you. But right now, this is mostly designed to spit out a sequence that can be synthesized.
Have you been able to learn any rules about, obviously there's a lot of empirical data.
Sure.
But have you been able to leverage that and learn any sort of rules that don't and different factors that end up somewhere?
We're starting. So we're able to validate things that are kind of obvious. Signal sequences are always up front. You know, when you have a his tag or something, that's always going to be here or there. We're figuring out what those algorithms look like, and kind of the fun part is once you figure out what those algorithms are, it almost doesn't matter what the question that you're asking is. And so if you validate it on one thing in general, we're asking, can we figure out what a transmembrane domain looks like, and then therefore what is going to be on which side of the membrane. Those things are starting to show up in our data, which is nice that they do. And we'd like to see what else we can find in there. All right, thank you.
All right. Thank you for an awesome talk, Justin. I think let's take a few-minute break just to give people time to use the restroom or anything. So let's come back in 5 minutes and we'll get started with our last talk of the evening. Thank you.
So after it's unfolded in itself, produces 4 or 5 different domains. It's a great idea. I get it all the time. So there are ways to do that. I don't know some of those structures that you mentioned. We have a bunch of there are things out there that I don't know about, like generative. There are various enzymes coincidentally. You kind of understand it. So you can have it as it will then do sort of work with that to understand what each of these like. Or you can get a binding very strong binding that you already use. You build protein A, use the binding thing. You build protein B with the corresponding now enzymes together. Okay. So we'll link these enzymes into the train. Another thing that's to see what's going on there. It's just more of like a non-linear analysis. Yeah, like expose this to many right? Yeah, I don't know. Just to get a better feeling for like how long certain things are polygon units. Yeah. So, what kind of properties are all the viruses, they have all the different shapes on platonic solids, and all of those are the single domain tiles. The library of tiles, say I run it.
Oh my God.
All the code is public. So these
unlike electronics, we have to go over the yeah, I did my first it's already
That's like a synthesis. Maybe it's like predicting that. Yeah.
That's how we have some malaria vaccines. They have
Oh yeah, I can see. Yeah, that's the most from this process. We use all the So they meet with us and the operation will be able to put together into so let's have some confidence. And then we'll see if there's a connection. I think there is. I don't know how. Is that hard? It's really good delivering machine learning. We're trying to get to the point where we're getting them past some machine learning. Yeah, that's what all this stuff around that. We only use yeah, the next thing will be able to. So it's a viral capsid. It's a capsid of a virus. So viral capsid. And everybody knows it's like a lot.
Begin.
And I think right left should now. All right, folks, let's go ahead and get started with the last talk of the evening. All right. So our last speaker will be Andy Corbus, who will tell us about some very cool work in digital medicine. So please take it away, Andy.
Thanks. Hey, so I'm Andy, and I'm a software engineer working with body-worn sensors and software as medicine. And so I know this talk is a little bit different probably from what most people have done in this session before, but what I wanted to tell you a little bit more about was this idea that which is, can an app replace drugs? And in many ways, it will do very similar things to the way that drugs work. So I wanted to introduce you to what that looks like. Okay, so I'm going to go through this concept of how doctors will treat patients, so measuring, diagnosing, and then treating. And then with this rise of software as medicine, talk about some of the ethical and regulatory challenges that people are facing, and then give an example of what this could mean for our future. So ideas of how you can do research at home and then decentralized clinical research. Okay, so this is 2005, meeting the Pope, and this is 2013. So I think this is something we all know. We have a lot of really powerful computation that sits very close to all of us, which is changing the game and is able to collect really interesting physiological and behavioral data on all of us. Here at some point owned like a Fitbit, Jawbone, something. Come on, some wearable? Okay, who's like actually wearing it today? So most people drop off on a lot of the wearables after about 6 months, and I think part of the reason why that happens is you get so much data, and then what do you do with it? And this is the same problem with a lot of doctors too. Like, you can track your blood sugar at home, you can track your weight at home, and doctors are like, busy, I don't want to have all this information all the time. And so I think wearables have had a pretty bad rap up until about like the last year or so ago, when we've been able to do some really interesting things where wearables don't just mean wellness data, but you can really start tracking clinical grade data on this. Speech that Steve Jobs, that's ironic, but that Apple just gave, they first announced that they were starting to partner with the FDA to track more clinical grade data on this. So today I'm going to talk to you about a couple, there's going to be like some jargon, but just to introduce you to it. So this idea of using sensors to measure data is increasingly being called digital biomarkers. And then when you take all this data and you make a clinical decision, digital diagnostics, and then to use software itself to treat somebody is called a digital therapeutic. Okay, so these are some examples of digital biomarkers. You've probably already worn them before. So Fitbits, tracking EKG, tracking your heart rate. There's some of them that are purely just software, and some of them are combinations of software and sensors. If you have an Apple Watch, you can download Cardiogram. Cardiogram's really interesting because it takes the 2 trillion Apple Watch heart rate data and moves it into something that you can actually make clinically useful. So they have a 97% accuracy of detecting AFib, which is an abnormal heart condition. The thing that I really love about this team is that they weren't started through, they've partnered with medical professionals, but the core team was originally the founders of SIF Science, which, as many of you probably know, is a data company that was detecting fraud. So a lot of these questions that we have in healthcare can start to get answered using, using tools from other sorts of industries. Okay, so this is another favorite of mine. This is called a live core. So a live core is a single lead EKG. EKGs cost about $15K. A live core you can buy for $99, and it is FDA approved. And you can use that at home. Okay, so what I'm working on right now is that there's a ton of different sensors that are coming out, and it's really hard to cut through the noise of like what's real, what's FDA approved, what's not, like what's wellness. And so I'm starting to work on building a registry for these devices. So at the end, if this is something that you're interested in and want to start helping build the registry, a place where we're starting is with neurological disorders. So the phone's a really interesting way. Like if someone has tremor and you're trying to measure that, like just visually, it's like not really that interesting. And the gold standards that we have for neurological is really not that good. When on the phone, you can start to get a digital representation of that. And one example, which I've always found to be kind of funny, is like all the issues when you're building an algorithm that ends up getting really tricky. So, so Michael J. Fox Foundation was doing a phase 2 clinical trial with one of these digital biomarkers in the Netherlands. And they found that this biomarker was doing a much better job of predicting in-clinic, and they're able to represent it in ways that they haven't been able to do it before. But then when they went home, the people in the trial had like 20x more tremors than they normally would. And they're like, what is going on? And they realized that everyone rides on bikes. And so like when you're going down the cobblestone, it was not doing a good job of figuring out tremor versus like the cobblestone. It's like a lot of things that we need to say that like, of course, algorithms aren't going to solve everything. And we have to build like smart algorithms. So maybe for that one, having GPS and speed along with the tremor is going to be able to separate biking versus not. So there's still a lot we need to learn. And then this was published yesterday. Tom Insel is one of the leaders on behavioral and mental health, and he's creating what he's calling digital phenotyping, where he's using the cell phone to have a better sense of whether or not somebody is a mental health episode or not. So I can share this with you later. Okay. So it's interesting, maybe we can track information, maybe we can make a clinical diagnosis, but like, can software actually treat someone? And it turns out that it can. And this is what's called digital therapeutics. So within this category of digital therapeutics, there's generally 2 places that are the most common. So one is when you use software to manage your behavior. And you've already probably all seen software manage your behavior in ways that you probably don't want, like you're constantly checking Facebook and like doing the infinite scroll. And so there are ways that we can use software to create more of the behaviors that we do want. And often those are using what's called cognitive behavioral therapy. And then the second type is when the software itself is therapeutically active. So I'll go in the first one. So with CBT, cognitive behavioral therapy, the FDA has already approved a app that's a prescription grade app for people who have diabetes. And the neat thing about this is often when somebody has diabetes, you have to go and have a weight loss coach, and you'll have also drugs that you're using to manage your diabetes. And like, no surprise, it's really hard to go and like actually go to the weight loss program in person, and tracking everything is like really not that useful for people. So these had a 65% desired weight loss in the population, when the in-person like weight loss coaching has about a 12% over a given year. We're really able to like touch people in a much more meaningful way with these. And the thing that's really exciting about the WellDoc one is that insurers are paying for it now. So they you can actually get like a full prescription off of an app. Okay, the other one that was neat is just last week the FDA another one, which is for alcohol, cocaine, and marijuana addiction, and they'll likely be doing a second version with them on the opioid crisis. Okay, so that's managing behavior. The second is like, can software itself change your brain structure? And this is the class that's called therapeutically active. So how many people here play video games? At some point. How many people told you that your like brain was going to rot by playing video games? Awesome. You can now be vindicated and say like, there's prescription video games that are going to be helping my brain. And in fact, if you get this talk afterwards, there's a great TED talk that shows that the brain of gamers looks different from non-gamers in a pretty meaningful way, and that's good for you, so you can see it. So NeuroRacer came out of UCSF. It was Adam Ghazali's lab, and he was looking at the brains of people between 65 and 80. And he found that when people played the NeuroRacer game for about 4 weeks, to 80-year-olds had brain structures that were similar to 20-year-olds. And so what this game is able to do is it's able to reform part of the prefrontal cortex and really use what we've been learning with neuroplasticity to like rebuild parts of the brain that that people have historically been losing. So it's you use your brain or you lose it. And so there are early indications that we can start to use it in a meaningful way. That I interned with when I was in grad school took this technology out of Adam Ghazali's lab, and they're using it for pediatric ADHD. And so right now they're in phase 3 clinical trials with the FDA for pediatric ADHD, and it looks like we'll know next month or two, but they're most likely going to be the first prescription non-drug treatment for ADHD. Okay, so if we can change the brain, should we? And this is a lightning talk, so I can't go into it too much, but there's a whole branch of neuroethics around this. So if there are ways that we can start changing the brain, of course, in the context of healthcare, everyone says yes, but under what conditions can we tap into somebody's brain and change it in a way that they might not want? And then what is the FDA doing about all of this? So there's a ton of good research that shows that a lot of the digital therapeutics work, but as I was talking, if anyone thought about Lumosity and said like, hey, isn't this kind of a scam? It turns out with any good technologies, there's a lot of people who use marketing and don't have good scientific rigor. So it's pretty hard for people right now until you have a regulatory body that shows what's real and what's not to draw those lines. And so what's happening with digital therapeutics is similar to what happened with drugs, where you have prescription drugs that are rigorously tested, and then you have vitamins, which are like based on science, but like unclear if they work or not. And so the challenge that we've had right now is most of the things that have come out in digital health have been in the vitamin category and not in the prescription category. But last year, FDA spun out a new software group. So within devices, they spun out a group that's just looking at algorithms. So if you think about a company like Akili that is developing this game for pediatric ADHD, do you really want them regulating the iPad? Or do you want them regulating the software and the algorithm on the iPad that is changing the way the kid plays the game? And I would say I want them regulating the algorithm. I don't really want them regulating the iPad. But the FDA wasn't set up to look at those sorts of things. And so for anyone who's also developing any sort of ML for detecting breast cancer and thing where it's the algorithm is making a clinical decision, we really need our regulators to be thinking about like the algorithm and not just the device. And so they came out, they realized this too. So they came out with this thing called SAMD, which is software as a medical device. This is a really ugly graph, but I got it from the FDA. And so on this side is like software that we all know in healthcare, where it just is like retrieving information or just processing information. And this is like your EMR or things that are collecting things using software. That's not a medical device. And then all of the other side is what the FDA was familiar with software. So like pacemakers. So software is powered devices, but it hasn't actually been this middle part where it's making a clinical decision or in a closed loop where it's providing a therapy. So they've now started to segment out this middle. Okay, so there's more here, but come up to me afterwards. I'll do a quick version of it. So what this means for clinical research is pretty interesting. Right now, most clinical research, you have to go into a lab and or into a clinic and do your blood draws there or sleep in some weird bed hooked up to all the wires in there. And like, obviously, you're not going to have a normal night's sleep in that sort of situation. So there's a bunch of companies that are working on what's called remote trials where you can start doing more data at home. And the cool thing about remote trials too is you can start doing these N of 1 studies, like citizen science-based studies, because like I might not really care what it looks like for like me compared to an average population. I kind of want to know how something performs either to people who are just like me or to myself historically. And we've never really been able to track that level of information before, but now we can. Okay. And then the last one to give some food for thought around this is decentralized systems, which is a whole kind of like another talk. But if we're going to have all these IoT devices all over the place and we're going to be collecting mass amounts of data, we want to make sure that we can trust that this data is accurate. And in healthcare, we spend a lot of time talking about data confidentiality, which is like, we're going to make sure we follow HIPAA and we'll have encryption and you're not going to be able to access my data. But increasingly what matters more is data integrity, which is, can you change or manipulate the data over time? And so I might not care that you all know my blood type's O positive, or if someone could go in, switch my blood type to be negative right before my surgery and leave no trace. And so if you think about systems like any decentralized system like Ethereum or whichever that can do time-stamped based audits, and you can start to have a system where everybody agrees on whether or not a piece of data has been changed or not, it can start to be really important. And we might want even more of that, given that most of this data is going to be collected off of small little devices that we want to make sure that we trust. Okay, so my plea is that I think in Silicon Valley that we think all technology is good technology. I think that's not true. Like with nuclear weapons comes nuclear power. So like two sides to all the things that we work on. And if we just like blindly run and just develop anything, we can end up in a future that we don't necessarily want. And I don't think that we can slow down the future. So it's going to be important for us, particularly as things are tracking more of our own biological data, to think about like which version of this future we want to create. That's it.
Do you know anything about the placebo effect? Is there such thing as software somatic effect?
Yeah, well, I mean, the thing that's interesting about the placebo effect is it's real, right?
It is.
Like, you know, it's actually a
So why
result
not
from it.
software, right?
Yeah.
Okay. But is there any app that do something or attempt to do something like that?
I think this is actually one of the really tricky things with some of the software is that it's hard to sometimes to piece out the placebo effect because you might get the outcomes you want, and then is it because people just believe that they were going to have that outcome or listen to the software? And it doesn't matter. Yeah. Yeah. I think
it, like you could do the usual kinds of controls. You can have this FDA description game,
yeah,
and then you can just have Mario Brothers or something.
Yeah, so that's actually that's the structure of the Achilles game. So they have their software, and then they have this other like word game that they're comparing it against. Which I think is a little bit different from placebo effect, because in the placebo effect, it's that somebody might think that they're having that response, and then they still get. I mean, I guess if you're creating two separate things.
It was double blind, or the person giving out the game.
Yeah, which game you have. Mm-hmm. Yeah. Yeah, it's perfect.
Has FDA indicated that they want to move to the lower end, that could analytic algorithms, things like that, or are they hesitant, or are they?
No, they really want to.
They really want to.
Yeah, it's actually interesting. So the FDA, now that they have this software group, which is headed by Bakul Patel, which you can look up his things online. The thing that is kind of funny with it is that the pharma companies are actually the ones that are really slow to develop all of these things. So in many ways, the FDA is like, please do this. It's really exciting. And one example of it, which as a software developer, I think is really neat. Maybe last month, they released what's called a pre-cert program, which is that they're going to pre-certify companies rather than products. As a developer, to continue to do development during the FDA review. Because can you imagine if you had to like stop your code like review 2 years like during that process? Like, you know, everything's moving so fast. You'd be like shipping something with a BlackBerry. Yeah. Yes.
So the FDA slide you had up there. So I saw like a fourth type. So are they bringing down the risk level for these kind of devices, since it's not under the medical device category? I'm just trying to understand, you know, that normally they want everything, you know, the version of the iPhone, everything like locked down. how are they getting away from that area that is on everything locked down?
Yeah, so I'm not with the FDA, so I don't want to like speak on their behalf, but my understanding of it is the FDA wants to make sure that things are accurate and reproducible, and they balance safety with efficacy. And so thankfully for most of these things, there's not as many safety issues, if that's like what you mean by
That's what I
risk.
meant by risk. Yeah.
Yeah.
So it's a lower level risk, so they're allowing a new guidance for this area.
Yeah, so since like the harm to the human, like the safety issue is not as much as like taking a pill or like having hip implant. They are making faster tracks, like this pre-cert program, which is like they're calling it the TSA pre-check of it. I think they have a very high bar for efficacy still. So I think that's probably like the big hurdle that people have to go through. And a lot of these digital health companies aren't going through the FDA. So some are because they want to get prescription and they like the trust model, which you might have heard of, which is a popular one in this city. They're going after pre-diabetes. And since that's not a clinical, like it's not diabetes, they can sell directly to self-insurers. And then self-insurers pay them based, I think, right now on a risk-based payment, and they don't have FDA clearance. So there's different business models people can take. Yeah, which part of clinical trials?
Oh, the slide that you had about the N-of-1.
Yeah, so I don't think anyone in clinical trials will use the term N-of-1, but yeah, so over the process of, this is something that we had put together online. So over the process of doing clinical research, software is kind of like eating each of the chunks of that. Like how do we design the protocol? There's different ways using software. You can better crowdsource protocols, patient recruitment. You've probably seen a ton of different companies popping up of how to recruit patients, collecting all of the data. There's all different ways that you can start like really using software to have better clinical trials. And I was just as a side note, I was at a pharma conference last week, and 40% of clinical trials don't even have e-consent, which means that even if you're in the clinic, you still have to sign a physical piece of paper to sign up for the trial, like no software at all, like from the 90s or 80s. And so these virtual trials are collecting data outside of the clinic. Sometimes they're called siteless trials. People don't really know what to call these things yet. They're collecting different sets of information. With some of them, you might be able to do N-of-1 studies, like medical. You can create your own app on there. Mostly they're selling directly to researchers or to pharma companies or sponsors generally. Yeah. Yeah.
How is software as a medicine interacting with the doctor-patient interactions? Is there follow-up? Is there any interaction process?
Yeah, I think this is still very much being figured out. So with Achilles, it's interesting when you get the data back because you'll need to have different platforms. So like right now, Achilles gets the data back to see how the child's performing. They're also creating a dashboard so that the doctor can interact with that. And then also parents and children, because else we just like suck up the data and never really give back any information that people are participating. This allows you to give back data, but that also gives the question like, should you? Does that change the type of trial? Like when do you give it back? So I don't know if that, I think people are still figuring it out. It probably depends on which piece of software for the doctor patient. And if you're thinking about new companies, imagine what a pharmacy is going to look like in the future. Is going to be really important for that doctor-patient relationship.
So once I think that's software approved, is it possible that I could also get like a book approved? So the book could tell you kids to do stuff, you could follow the instructions in the book, check off. Why are there no book approved prescription books? Or does that exist?
Yeah, I think they kind of do. So like cognitive behavioral therapy, like these therapeutic treatments where like a therapist will give that to you, is some of those are often like very more rigidly prescribed. Yeah.
That's a professional doing it.
Yeah.
I'm just sort of curious how what this opened up, like it opens up other things that aren't software.
Yeah.
You get the doctor to sign that book or the author?
Or like in the Wild West for a lot of unknown.
Yeah, it's just fascinating.
You can get a bunch of people to buy books. I bet people will be really excited about that.
Sure.
You mentioned the use of these devices dropping off. How do you, like, within 6 months, right?
Yeah.
How do you envision either like motivating or like, you know, keeping people, you know, up to date with wearing their watches, or they're using their phone regularly, things like that?
Yeah, I think part of the issue is that you're kind of given like this massive data and you're not really told like what it means or benchmarks or anything. And that's because a lot of the companies have been really nervous to say something because they'll get fined by the FCC if they make a claim that's not a clinical claim. I think this opens up the opportunity for you to get like meaningful data back. So like maybe if you knew that you had sleep apnea, if you use the product and it could actually say like, hey, your snoring is actually apnea at night, you might be more likely to use it. So I think having going to be helpful for people. And I have a lot of other thoughts around like what we call gamification or encouraging it to be part of life is probably like a whole really interesting user experience. And then the other one I think is going to be important is these things need to be like more passive. So if you could charge it like every night, like the Apple Watch, or even every couple hours, like no one's going to use that. So the more that we can integrate it, even like the watch itself, or like if your glasses are able to do that, or sitting like passively in your bed or something like that, I think anything that is more invisible will be better for collecting. Yeah, what am I wearing? I mean, this is not an endorsement. This is mostly Andrea testing like random stuff, but I'm wearing a very old Apple Watch and a Fitbit, and they both have different heart rates, which I find to be funny because that's probably like the easiest thing, just like how many times my heart beating per minute. Yeah, so I've just been kind of testing different stuff. The other one I like is the Bedit. I don't know if anyone uses this one. It's a sensor that goes under your bed. You use that one?
Really?
Oh, you're in Project Baseline. No, I've never seen that one.
I just meant like not the physical thing that you're using, but what are you monitoring about yourself?
Mostly I've been interested in my sleep and measuring things with my sleep. I travel a lot for work and I kind of messed up my sleep cycle pretty substantially. So I got interested in this because I was doing a virtual trial with a company called Sleepio. And they were able to, like, it's a CBT-based app that was able to, like, completely reshift my sleep. I was waking up, like, something crazy, like, 14 times a night, but would go right back to sleep again. It was annoying because I just was, like, not sleeping through. And then I used the app, and then I now wake up, like, 2 or 3 times, which is apparently, like, the average human. Most people don't recognize it.
How did the behavior change? How did they get you to change your behavior?
I'll have to talk to you after. It was a 6-week course.
How much?
Yeah.
How much for sure? How much do you wish that more invasive measurements? Like I've heard people that use glucometers to keep their glucose level in check, even though they don't have diabetes, so that they can fast longer. And how to integrating that with software? How much is?
Yeah, this gets to like a bigger thing, which is I think it's pretty interesting how we call like certain things like what we today call like mental health, and then we have other things we call human augmentation. And like, where did we actually draw the line between like what's sickness and what's health? You know, like everything's kind of like spectrum based, and you might want to be on different parts of the spectrum. And I think there's a lot of people that are working, especially in Silicon Valley, on the augmentation piece that starts to feed back into the maybe care piece, and then care kind of feeds back into augmentation. But yeah.
How is the FDA regulating the training data distribution for these models? Because like there's no Panasonic face detectors when working with electricity. And I can imagine the same problem occurring here when you have data sets that are just biased from and you just start studying that software everywhere else. Also self-selection.
Yeah.
And you have using and all your population becomes biased towards either those that are too sick or too healthy, and now you have like everybody who's being told not to get sick or
I think the first thing is this is not a new problem for the FDA. So like a classic example of this was Ambien was only tested on men, and women metabolize Ambien really differently. So after they released Ambien to the public, the rates of car crashes for women skyrocketed. And so the FDA had, and obviously then had to realize that and did a recall and then change. But the fact that we don't have, only 5% of the population right now participates in clinical research, and women and minorities, even in drug trials, are severely underrepresented. So it's two parts. One, having these virtual things allows more people to be part of it. So this is a question the FDA has struggled with even on the drug side. The fact that you're interested in, they have a paper out for comment for either just closed on how to handle some of the biases, because they're particularly worried about a lot of the ML. You can't even really dig into like how something's making a decision there, right? Like the pattern. So yeah, if you're interested, they'd love to hear what you think. Yeah.
All right. So let's thank Amy one more time for great talk. And that concludes kind of the formal set of things for this evening, but feel free to stick around. We have the room till 7:30. I think there's still leftover pizza. Feel free to grab some. It's probably going to trash if you don't take it. So mingle, please hang around for a bit, and thank you all for coming out. And let's give the speakers one more round of applause.
Also, if anyone's going to San Francisco and I could carpool with you, that would be awesome. So just let me know. Yeah. I mean, there's so many cool stuff. You don't need it. Yeah, if you have this background. Yeah, now you're going on. You are? Yeah. Yes, thank you. I'm Abscess? Yeah, I'm I didn't know any of this last week. Yeah. How'd you get into like so I've been doing more healthcare work, and then I went to DeepChem later. Afterwards, because I used to do a lot of data centers, my thesis was in like metrics, and so I was doing like data and big healthcare data, yeah, like all sorts of like other stuff. And then I was like, I just want to be able to build the software all the way through. And I started to hear about these things that were digital therapeutics, and I was like, what software can you bring? This is crazy. Like I try to fix it. Yeah, I do it. I'm like, I'm smart. I know I am. Yeah. That's really interesting.
So what was the name of the professor at UCSF at Brain?
Yeah. You can go, yes, a thing called Neuroscape, that's big, and like, set you up on some of those stuff.
Oh, yeah?
Yeah, how old are you? We also have stuff where you can actually actually, I think it might be check it. Yeah. I think it he's running a ton of research.
So I would think that like that's going to stick.
And I know it's one of those things where like you probably should investigate it more, but then it's like running through between juggling walking around figuring a way to something else that like have to operate on some. I guess get a data set yeah, it's just kind of like I don't think that there's anything else that's been out there, already have the data to out that data for all everything else that that piece, there's a toolkit to work with, so